Okay, so we're getting back to this problem set. I'm skipping number 7. It's very algebraic. It takes a lot of manipulations. It might be one of the easier ones on the problem set, but it's just there's just a lot going on, and I don't want to do that on a video. It's kind of tedious and boring, so I'm skipping to number 8. Number 8, I'll read it to you. It says the differential equation for P shows that P prime of Z equals 0 if Z equals omega 1 over 2, omega 2 over 2, or omega 1 plus omega 2 over 2. These are the half periods that we've discussed before. The corresponding values of P, okay, have their own special names. Okay, so here's what we call these things. These are just the half periods. Okay, and we could write that differential equation for P of Z cubed minus G2 P of Z minus G3 of, minus G3, excuse me. We can write this, which if you remember was P prime of Z quantity squared. We can write this as 4 times P of Z minus E1 times P of Z minus E2 times P of Z, you guessed it, minus E3. Basically, this is a way, if you didn't know they were zeros and you didn't know what this was, you would be forcing zeros at each one of these points by plugging in these, right, at each one of the half periods. So, the question is, we want to show that this relation is true. And that's just a matter of differentiating this differential equation right here. Okay, so we're going to do that. We wind up with P prime of Z, P prime prime of Z. And another thing to note to make this really quick, when you take the derivative of 3 functions multiplied together, the product of 3 functions, what you get is something that looks like this. My daughters upstairs are playing. Right? It's just like the product rule, but there's 3 instead of 2. Okay, very simple. So what we're going to do is we're going to be looking at this. And we're going to kind of use this mindset here, this product of 3 rule, call it. And what we get is the derivative of any one of these 3 is going to be the same. It's going to be P prime of Z. So we get P prime of Z times P of Z minus E1 P of Z minus E2 plus P of Z minus E2 P of Z, oh shoot, I can salvage that, minus E3 plus P of Z minus E1 P of Z minus E3. Okay? All we're doing again is we're taking, the derivative of this one, multiplying it by these 2, derivative of this one, multiplying it by these 2, derivative of this one, multiplying it by these 2. And the derivative of any one of these is P prime of Z. So we see immediately that this can cancel, so to speak. And we can get rid of this 2 as well. So, rewriting. Maybe I won't rewrite, actually. Let's just stop for a second and take a look at this. Maybe I'll clean this up here. That's the better way to do this. We have 2 over here. We killed off all this stuff over here. Now what we're interested in is a value that looks like this. P prime prime of omega 1 over 2. So what is that? Well, I'm plugging in omega 1 over 2 anywhere I see a Z. So here, it's going to give me P of omega 1 over 2. But what is that? That's E1. So this entire thing here, this double term here is going to be 0. Same with this one. And I'm going to be left with 2 times E1 minus E2. This is the only one that survives. Minus E2 times E1 minus E3. Similarly, when I plug in omega 2, this one's going to go to 0. This one's going to go to 0. And this is going to be the only one that survives. E2 minus E1, E2 minus E3. Finally, scoot down a little bit. Finally, this is going to give me E3 when I plug it into P. So this one's going to go to 0. This one's going to go to 0. This is going to be the only term that survives. So E3 minus E1, E3 minus E2. There you go. Okay, so problem number 9. It says, according to exercise 4, and exercise 4 is the one that was talking about rational functions of P of z representing all even elliptic functions. It says, according to exercise 4, the function P of 2z is a rational function of P of z. Prove that, in fact, this expression here is true. Now this one's a little bit like 7, which I skipped, in that it requires some careful algebra, which I'm not going to do for you here, but I am going to in case that you're watching this. The whole reason I'm doing these videos on the problems is to kind of guide people who are learning by themselves. You know, without going off too much on my philosophy there, suffice it to say a lot of these problems you can't find answers for online. So I'm going to give you a really thorough hint, and you just stop it whenever you want me to. I'm going to work you all the way up until the point where you would have to do some really careful algebra, okay? So, starting, you remember the process for finding a rational function of P of z that represents a given even elliptic function looks like this. First of all, you represent all the poles as these kinds of things. You know, let's say the pole is BI. Okay? Right? As these sorts of terms with order. Okay? And so that's kind of what we're doing. The next thing you're going to do is you're going to make everything fit algebraically. So that your final function looks like what you need it to look like. And I'll get a little closer to that as we go on here, okay? So we start, that's a crappy line there. Hang on, I'm going to use my little line function to do this. Here we go, baby. Okay. So here I've got my parallelogram here, right? And this is the parallelogram for P of z. That did not take. Let's just cover that up. Make this a little bit neater. No, I don't want sticky keys. Shut up. Okay. Here's a parallelogram for P of z. Okay. You've seen this a whole bunch of times if you're watching these videos. Okay. And you remember, I mentioned this at one point in the video, and I also mentioned it in problem 8. There are these special points. They're called half points, or half periods. They're called half periods, they're not called half points. And when you plug these points, like omega 1 over 2 and omega 2 over 2 into P of z, you get these E1, E2, E3s, right? Well, what does P of z do versus P of 2z? Well, P of z has poles at every lattice point. But if you plug in 2 of z, it's going to get to those poles twice as fast, right? So it's going to have poles at every half lattice point. Okay? So if I start with this, right, I'm going to have a pole at omega 1 over 2. I'm going to have a pole at omega 2 over 2, omega 1 plus omega 2 over 2. So I could start by writing this, and I could even put P of z down here, but I don't think I need to, and I'll show you why. If we have P of 2z is some rational function of P of z, sorry. If we have that P of 2z is some rational function of P of z, that means there's a numerator and a denominator, right? And what we're talking about first with the poles is the denominator. So specifically Q of P of z. And all I need to do with this Q of P of z is just hit all the poles. And so I'm going to start by doing something like this. Now these are going to give me poles of order 2 at every single one of these points. At least 2, I should say. And notice that I could tessellate this over here, and I'd get these points. And I'd double up on that one. I could tessellate it down here, and I could get these points. Right? Doubling up on that one. So on and so forth. I could tessellate it over the whole complex plane, get every single pole I needed. Okay? This is all I really need. Now, if I just stick this integer in front here, okay, just put the 4 in front, you'll see that this is actually the same thing as P prime of z squared, which is that 4p of z cubed minus g2 P of z minus g3, right? So I have a good representation for my denominator. Now I also have P of 2z. So here's the way I'm going to operate. I need P of z, right? So what I do is I say, well, then this must be true, okay? And here's where that stanky algebra comes in. You break this into a Laurent series. You do the same for this, and then you multiply. And this is going to give you a nasty Laurent series that you're going to then write in terms of P of z. Just by taking out the biggest exponent factor you can, moving on to the next one. Taking out the biggest exponent factor you can, moving on to the next one. Again, it's not difficult stuff, but the last thing I want to do is screw something up in front of you, and so I'm not going to do this. It's very time consuming. It's very boring. However, I will say this. I shouldn't say it's boring. Do this as an exercise. Do it, because you'll see some fascinating numerical relationships just kind of popping up. It's very interesting to watch. Okay, it's almost like you're watching the composition of some things. Keep an eye open for cubes of numbers to pop up. Relations between squares, things like that. Very interesting things. But this is worth doing. I'm just not going to do it on a video. If you try it, hopefully you'll see why. Okay, so for this one, it says let omega 1, omega 2 be complex, and the ratio non-real. So in the back of your mind, be thinking elliptic. Okay, and let f of z be entire. Okay, so f of z is entire. And then assume there exists constants a and b such that this is true, that when you move by one period, you're actually multiplying f of z by some constant. When you move by the other period, you're multiplying f of z by some other constant. Okay? Prove that f of z, oops, I still have some mess from the problem before. Prove that f of z is this exponential type thing. Okay? So here's what we're going to do. We're going to start, man, I didn't clean this up very well at all, did I? Okay, so we're going to start by thinking about what f of z could be. And this is kind of in efforts for one direction. Let's say that f of 0 is a. And let's say we go over by in omega 1, okay? So we're looking at f of in omega 1. That's going to be a times little a to the n, right? Similarly, if we go up m omega 2, it's going to be a times little b to the m, right? Because I'm just taking steps each time I increase by a factor of beta, or scale by a factor of beta, or b. Sorry, not beta. Good Lord, it's early. I'm not done with my coffee yet. Classic basic bro thing to say. So, in other words, each time I'm increasing by 1 omega, I'm scaling by another factor of b. And here I'm taking n and m to be integers, as I would with elliptic functions. Okay? So, from this, I could see that if I go up by, let's say, f of like in omega 1 plus m omega 2, I get a times little a to the n, little b to the m. Okay? So I definitely have something exponential going on. What I'm going to do is I'm going to put a name on b in this function. Okay? I've already got a good candidate for a, and that's f of 0. All we know is that these exist, which means we don't have any kind of, there's not really any restrictions on them except that they happen to exist. Okay? So I'm going to play on that just a little bit. I'm going to force this function into this form. Okay? But I'm not going to assume f of z is this. I'm just going to say if f of z looked like this, what would it be? Okay? So let's say that f of z, assume f of z is a e to the bz, or f of 0 e to the bz. Okay? What's b? Okay? So I can plug this in and I can say, well, I've got f of n omega 1, and actually more specifically, I don't even need to do that. I've got f omega 1 is going to be a, okay? And that's going to be A, E, B, omega 1, because Z is omega 1, which means that A is going to be E, B, omega 1, which means that B is going to depend on A. Okay? It's going to be log A over omega 1. Similarly, I could show that B is log B over omega 2. So really what I'm saying is big B depends on all four of these things, or at least three of them, in the sense that if I had, let's say, omega 1, omega 2, and I picked an A, I could then find my B. Okay? And we're assuming that these things exist. The only way that that would work is if this A and B kind of followed through with this. So what we're going to do is we're going to set this B equal to both of these things, right? And we're going to kind of let B, little b, follow through with it. If we have an A, I'll just take one more second to explain this, because I know I'm not being clear. This process would look like this. Given omega 1, omega 2, okay? That means we have both of these. We pick an A. Then we have little b equals E times to the log A over omega 1 times omega 2. You see what I'm saying? I can find B given this stuff. Okay. Now, we're going to use this kind of this sort of interesting trick from complex analysis. And when you're dealing with entire functions, this is a good tool to have in your belt. What you do is because this is an entire function, we know, okay? We're going to kind of ignore, for now, this this linear scalar, okay? This big A, okay? And we're going to multiply f of z, not assuming that it's of this form, by e to the minus bz. Okay? And actually, I'm gonna take a step back and just be a little more clear about this. We're gonna call this g of z. So what am I doing? I'm multiplying f of z, not knowing that it's of this form. I'm not saying I know that it's of this form. I just know that it hits something of this form infinitely many times. I mean, that's obvious. That's clear. I'm just multiplying f of z by e to the minus bz. You do this a lot in complex analysis. This is a little different because we've also got something that looks pretty elliptic, but you'll see where I'm going with it, okay? Now, and I'm going to say b equals this ratio. It's actually kind of interesting, these ratios. I wonder if there's something kind of trigonometric about that. I bet you there is. Actually, I know there is, and it has a lot to do with what we're doing now. But here's what we're going to do. We're going to keep going and shut the hell up. Okay, so suppose that I considered something like this. Okay? Well, that's going to be e to the minus b z plus n omega 1 plus m omega 2 times f of z plus n omega 1 plus m omega 2. Well, by definition, I know what happens when I do this with f. I get little a to the n, little b to the m, f of z. Holding capital B to be this definition, what I get over here is e to the minus bz, little a to the minus n, little b to the minus m. These cancel, and I get e to the minus b f of z, which is in fact g of z. So I now have that g of z is doubly periodic, right? And I also have that g of z is entire, right? I assumed f of z is entire. E to the minus bz is entire. So their products are entire, right? Did I go down too low here? I think I did. So from these two things, now remember, entire functions are meromorphic. They just don't have any poles. So I have g of z is elliptic with no poles. So g of z is a constant. Now what does that mean? If g of z is a constant, that means that f of z has to be of the form a e to the b z. That's your proof. Okay, so the next one's pretty straightforward, and we're just going to find the Fourier series for a generic Eisenstein series G2K of tau. We're going to do this the same way that we found the Eisenstein series when we were looking at that. Excuse me, the Fourier series for the Eisenstein series when we were looking at that. So we're going to start with cotangent, right? And actually, we have these notes, so I'm just going to use them. Cotangent looks like this. Using m, where m is non-zero. 1 over tau plus m minus 1 over m. Take the derivative. Take the derivative like how many times? Let's see. Well, let's say repeatedly. Okay. And what we get right, we can see this side of it as well in our notes. Okay. Repeatedly, what we get is something of this form. Okay, we get 2k minus 1 factorial m is minus infinity 1 over tau plus m to the 2k. So this is something that looks a little bit like the G2K Eisenstein series. And on this side, what we get is minus 2 pi I to the 2k times this sum. Okay. What we want g to k of tau, which looks like this, or I guess m in non-zero. We're not looking at the omegas. We're looking at m and n not equal to 0, 0 specifically, of 1 over m plus n tau to the 2k. What we want is this, okay? That is not equal to this, so I'm going to remove that just so there's no confusion. So what we're going to do here is we're going to kind of get this by itself. Okay, so I'm going to divide this off. I'm not going to index this if this is all right with, well, actually I probably should. Probably should be very careful with indexes, actually. And let's say 2 pi I quantity to the 2k over 2k minus 1 factorial. Okay. You see how I'm doing this? I'm just moving I'm moving that 2k minus 1 quantity factorial to the other side. And now I have this. Now what I'm needing to do is I'm needing to get everything where m and n is non-zero over here. Right now I have one series of m. Okay. So what I'm going to do is I'm going to kind of take the essence of this and scoot it over, replacing tau with n tau. Okay? So here we go. I'm going to write this out and then come back. Okay, so the first line here, we're trying to find this Eisenstein series. And so I'm kind of abusing my notation here, but this is the notation that's similar to what Apostle uses. What we're saying is that this is sort of a double sum, but what we want to kind of grab here is that both of m and n can't be 0, okay? But we want to encapsulate everything else. So what we're going to do is we're going to kind of break it out into a couple of cases. The first one is we're just going to run m by itself from minus infinity to infinity. And what that's going to do is that's going to give us a situation where n is 0 and m's non-zero. The next thing we're going to do is we're going to run from 1 to infinity, both n and m, but we're going to consider both cases where n is negative and positive. Okay? And we're going to use, first of all, the definition of the zeta function here. This winds up being, oh, I'm sorry, m can't be 0 here, right? Otherwise, then both would be 0. So this is 2 times zeta of 2k. Okay. And this here, this winds up just being 2 times this positive case here. So we now have something that, oops, did I mess this up? I think I did. M here is supposed to be minus infinity, I believe. Yeah. There we go. That makes sense. So now we have something that kind of looks like this here. Okay. Where we're replacing tau with n tau. Okay. So we rewrite our zeta here. And we have, did I leave this out? No, I didn't. We have 2 pi I 2k over 2k minus 1 factorial and we're summing. There's two of these. We're summing over in, okay, and R of E2 pi I R in tau. Okay. Now, okay. Now, this part I can just rewrite. Here's where this little trick comes in. I'm going to write everything up until this sum. What I'm doing here is I'm summing over both in and r, and I see that I have this factor r in here. And I've also got over here something with r over here. So if I were to call, let's call capital N Rn, but what they really do is they call little n Rn, but I don't want to be confusing. If I set the product Rn equal to n, so just a quick example, let's say 6 equals r times n, okay? What could Rn be? Well, it could be 6, 1, it could be 3, 2, it could be 2, 3, it could be 1, 6, right? Pretty much any combination that gives us 6, right? But what am I doing if I'm looking just at one of these columns, specifically R? I'm considering all of the divisors of 6, right? And then I'm plugging them into this function of R. So what I'm doing is I'm considering all divisors, looking at the sum of all divisors of n to the 2k minus 1. Okay, well this actually has a name. It's sum of divisors with this little subscript here. And now I can rewrite this, that's n. Now I can rewrite this as e to the 2 pi I in tau. And this is what I have up top here. I think they used little n, as I said before. But this is how you get it. And this is how this wanky sum of divisors thing comes in. You're just combining two, and you have this little power here. So, okay, so for this one, we're just looking to show that g2k of minus 1 over tau is equal to 2 to the tau to the 2k times g2k of tau. What does this look like to you? This is one of the transformations that we've been considering as part of the modular group. This is the transformation S acting on tau, right, as a Möbius transformation. The easiest way to see this is by looking at the definition of the Eisenstein series. Okay. So here we have it. And I've screwed it up already. I'm sorry. This is maybe I'll just do this actually. This is g2k of tau. So what is g2k of minus 1 over tau? Well, that is mn non-zero of 1 over m plus n over tau, 2k. Okay. What if I multiply both the top and the bottom by tau to the 2k? Well, then I get a factor of 2k out here, right? M n non-zero of 1 over n tau plus m tau plus n 2k. To the 2k. But this, of course, because we're summing over all of these, is the same as if I had used n instead of m. I'm just swapping these. They're doing precisely the same thing. So I get my result here just by kind of finagling with this. You could try to do it with the Fourier series. I couldn't find a very intuitive way of doing that. Maybe somebody out there can think of that. I'm sure it has to do with complex geometry if there is one. The problem that I kept coming up with is trying to do it with the Fourier series is that zeta function you have out in front. It seems to kind of block you from doing any good algebra, and it doesn't make a lot of sense anyway. So this is really straightforward. It's one line, basically. Now we're going to use this to find a good representation of this. I over 2, if I act on I over 2 with S, what I get is minus 2 over I. Minus 1 over I is just I, so we have 2I here. And if we're considering 2I to the 2k, right, we can even simplify that further. We can say that that's minus 4 to the k, g2k of 2I. The next one is g2k of I. Well, S acting on I is minus 1 over I, which doesn't change it, it's just I. So what this says is that this equals I to the 2k, g2k I. Well, for odd k, that would mean that g2k equals minus g2k, which of course means g2ki is 0.